Point set topology provides a rigorous framework for defining spaces based entirely on their collections of open sets. When we take two finite topological spaces, X and Y, and combine them into a Cartesian product, we need a reliable way to define the open sets of this new combined space. This diagram illustrates the standard method. Instead of listing every open set in the product space, we use a basis, a smaller collection of sets that generates the entire topology. For the product of X and Y, a basis element is constructed by taking an open set U from X, an open set V from Y, and taking their Cartesian product, yielding the open rectangle U cross V. In finite dimensions, this structure behaves highly predictable. If you have a function mapping into this 2D product space, and its individual coordinate functions are continuous, then the combined mapping into the product space is guaranteed to be continuous. The rules of continuity map cleanly over finite products. However, taking these exact axioms and scaling them to infinite dimensions without adjustment produces mathematical contradictions that break the foundations of continuous mapping. Watch what happens when we move to R omega. This is the countably infinite Cartesian product of the real line. Instead of points in a 2D plane, an element in R omega is an infinite sequence of real numbers. The intuitive leap most mathematicians first make is to define the basis elements here exactly as we did in 2 dimensions. We take an open interval on the first line, another open interval on the second, and continue this pattern across every single dimension to infinity. This generates what is known as the box topology. Its basis consists of all sets formed by the infinite product of open sets, where every single U alpha is an open interval in its respective coordinate space. By enforcing a strict boundary on every single one of its infinite coordinates, the box topology generates an enormous surplus of incredibly restrictive open sets. This density of constraints will eventually sever the continuity of basic geometric functions. To build a topology that survives infinite scaling, we have to construct it from the ground up using projection maps. A projection map takes an infinite sequence and isolates its value on a single coordinate axis. We use these projections to define a subbasis. A subbasis element isolates an open interval on exactly one specific axis, leaving all other infinite axes completely unconstrained. The crucial step happens next. To form a proper basis element, we take a finite intersection of these subbasis elements. The resulting shape restricts only a finite number of coordinates, while the remaining infinite sequence of coordinates equals the entire real line. This specific construction is called the product topology. By deliberately leaving all but a finite number of dimensions completely unrestricted, we build a space mathematically engineered to preserve continuity. This infographic shows extreme structural difference. On the left, the box topology restricts every dimension. On the right, the product topology restricts only 3, leaving the rest as the full set R. Because every basis element of the product topology can be contained within a box topology basis element, but not vice versa, the box topology is strictly finer. It contains a vastly larger collection of open sets. For a function to be continuous, the inverse image of every open set in the target space must be an open set in the domain. When your target space is a finer topology, you have significantly more open sets to test. This reveals a counterintuitive reality of infinite spaces.
Having a finer topology with more open sets makes it much harder for functions mapping into that space to maintain continuity. The strict constraints of the box topology create targets too narrow to hit. We can test this boundary by mapping a simple line into R omega. Consider a diagonal map, f of t, from the real numbers into the infinite product space, defined by the sequence t, 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 and so on. Let's look at the individual coordinate functions. For every index n, the coordinate function is simply f sub n of t equals t. This is a standard identity function, mapping R to R, which is demonstrably continuous. According to the rules of standard finite spaces, if all the individual coordinate functions are continuous, the combined mapping into the product space should also be continuous. To see if that holds true in the box topology, we select a highly specific basis element for our target. Let B be the product of intervals defined by -1 over n to +1 over n. As we progress down the infinite sequence of axes, n increases, which progressively shrinks the allowed interval tighter and tighter around 0. Projecting a perfectly continuous diagonal line into this specific, infinitely shrinking box reveals a mathematical contradiction. The definition of continuity requires that the pre-image of our target basis element B, the set of all inputs that map inside B, must be an open set on the real number line. Our diagonal map sends the input 0 to the origin coordinate, 0, 0, 0, and so on, which is inside B. For the pre-image to be an open set, it must contain some open interval around 0, defined by a positive boundary we will call delta. Because f of t maps a number directly to itself across every coordinate, the entire interval from negative delta to positive delta must fit strictly inside the interval negative 1 over n to 1 over n on every single infinite axis. As n approaches infinity, the fraction 1 over n shrinks toward 0. There is no positive real number delta that can possibly be smaller than 1 over n for every integer n. The only input that actually fits inside all of these infinitely shrinking boundaries is the number 0 itself. The pre-image collapses from an open interval down to a single point. A single point is a closed set. The inverse image is not open, therefore the function is not continuous. The box topology imposes infinite restrictions that isolate points too severely, breaking the continuity of a straight line. Now we retest this exact same diagonal map using a basis element from the product topology. This target restricts the intervals on a finite number of lines, in this case 3, and leaves all subsequent lines completely unrestricted. Finding a valid delta for this pre-image is now an entirely solvable operation. The mapped interval satisfies the first 3 conditions and easily passes through the infinite unrestricted dimensions without ever getting pinched. Because the product topology only restricts finitely many coordinates, we only need to find the minimum of a finite set of delta values. The minimum of a finite set of positive numbers is always a positive number. A valid open interval is guaranteed to exist. This establishes Theorem 3.4. A function mapping into a product space equipped with the product topology is continuous if and only if each of its coordinate functions is continuous. By utilizing projection maps to purposefully restrict only a finite number of dimensions, the product topology preserves the categorical behavior of limits and continuity. It proves that to navigate infinite dimensions, you must leave the infinite mostly untouched.